Hello and welcome to chapter 5 of CHEM25, which is about gases. Okay, so first of all, what is the importance of gases? As you know, there are three distinct physical states. We have gases, liquids, and solids. And out of these three, gases are the simplest to describe. Why? Because the distance between molecules and a gas is very large. Therefore, we can say that there is no interaction or very little interaction between gas molecules. And this means that we can study the gases, the molecules, one by one. Okay, so instead of having to take into account the interactions that are within a molecule and between molecule, we can just focus on the interactions within a molecule. So for example, I'm a gas-phase physical chemist, and so when we study molecules, or actually we do study ions, then these ions are isolated from each other in the gas phase, and therefore they are the simplest to describe experimentally and also theoretically, because the interactions only within the molecule are taken into account. But of course, you know that gases are important in their own right. Well, we have the atmosphere here, right? And the atmosphere of the Earth is crucial for a number of reasons for our survival, right? I mean, now there's a lot of talk about climate change. Then there was a big issue with the ozone hole, essentially that the concentration of the ozone was depleted. And since the ozone was protecting us from certain kind of UV radiation, this was a big health issue. And of course, if you come from LA or better from Beijing, then you know that smog is a huge issue. Air pollution is a big thing. And in chemistry too, several chemical reactions, they go in a gas phase or they produce products that are in a gas phase. And so there are lots of reasons for us to study gases. And then also this gases chapter will show you that there are some very simple laws that we can use, that we can learn, and then we can put them into calculations. So some of the early experiments that were carried out on gases, Van Helmont, for example, studied carbon dioxide a lot. He determined that it's similar to air, but it is not air. Okay, so originally gases and air, they were taken as one, but then discovering that there are other gases that are not air, definitely not air, is a huge step forward. And then the Flemish word actually for chaos, that's what it went into our word for gas, right? So the molecules, they are in chaotic mode, they're not as neatly organized as in a solid. Then Torricelli was the one who built the first barometer, and he was the one who determined that the air in the atmosphere exerts pressure on us, and then he could measure the pressure. And then no secret then that the word torr, one of the pressure units, which is actually millimers of mercury, is coming from his name. Then Otto von Guericke in the early 1600s invented an actual vacuum pump, and so he was able to remove air from a significant volume. And you probably know that experiment in which you put two hemispheres together, and then if you have air in there, then little baby can pull them apart. But if you pump the air out and there's vacuum inside, and the outside force of the atmosphere pushes it together, then even several horses cannot draw them apart. Now, when we talk about gases, the first thing that we absolutely have to talk about is the pressure and how to measure the pressure. So first of all, what is pressure? You know that pressure is force over area. Okay, and then the force is measured in newtons, and then the area is measured in meters square, and therefore the unit, the SI unit of pressure, has to be the SI unit of force, which is newton, and the SI unit of area, which is square meters. It's newton over square meter. And then this is the unit that we call Pascal. So Pascal is the SI unit for pressure. But the first units that were actually used were based on mercury. Why mercury? Because mercury is very inert for the most part. It's a liquid with a very, very high density. And so in order to measure pressure, you don't need to use as much. And we already saw on the previous slide, then here you have a 760 millimeters. How long is that? That's about 3/4 of a meter, right? So that's a very high amount of, well, very high line of a liquid. And still, because the mercury has a high density. If it was water, then it would have to be 10 meters high, right? And so therefore, with mercury, you can measure the pressure, and then the first unit could be millimers of mercury, or in this country, inches of mercury is also a unit that they use in aviation, for example. So torr is synonymous with millimeters of mercury, and then one standard atmosphere, right? So an average pressure value for our atmosphere at main sea level is 760 milliliters of mercury, or 760 torr. So this is one conversion that you actually have to memorize, right? So that one atmosphere is 760 torrs. Now, as I said, the SI pressure unit is the Pascal. So how much is a Pascal? Well, unfortunately, that's the main reason why Pascal is not a very good unit for measuring pressure at atmospheric pressures, is that a very small unit. So for 1 atmosphere, you need 101,325 pascals, or roughly 10 to the 5th pascals. Now, if you want to have a unit that is convenient, right size, right? So around 1 at an atmosphere, but it's also a round number in SI units, then you can go to the bar. Okay, well, don't go to the bar because you're under 21, but a bar is 10 to the 5th pascals, right? So it's exactly 100,000 pascals. And in fact, we've seen this unit before. Oh no, we haven't, maybe. We will see this unit in the equilibrium chapter, because this is going to be the standard unit that we put in into the equilibrium constant when we're talking about gases. Okay, so the book also uses torr to express pressure, but torr is certainly not the international unit, but just if you do the conversion, then it's 133 pascals. You can use the conversion between Pascal and atmosphere, right? This one, and then between torr and atmosphere. So 1 atmosphere is 760 torrs. Okay, so we will do some conversions here and there, but for the most part, the book uses atmospheres as the principal pressure unit. The standard pressure unit is the bar. The SI unit is the Pascal. In aviation, use inches of mercury. So there are lots of units. In fact, when you measure vacuum, so I work a lot with vacuum pumps, and depending on where you buy the instrument, in fact, it's the exact same instrument. If it's sold in Europe, then they use millibars for the pressure for vacuums, and then if it's sold in the US, then they use torrs as the pressure, even though it's the same unit, just the display is set differently. So how can you measure pressure? Okay, so imagine that you have a volume, some container that contains a gas, and you want to measure its pressure. So how can you do that? Well, you can measure it in relation to the atmospheric pressure. How can you do that? Well, let's look at the first one. So here is where we have the gas, and it exerts a certain pressure. Now, you know that a certain line, certain column of a liquid exerts pressure because of gravity, right? And that is the H times G, right? So the amount of mercury, if we want to measure the pressure in millimeters of mercury, then you just simply have to measure this H in millimeters or inches. And so what you do is the pressure of the gas plus the mercury pressure, that is how many millimeters you have. The two together have to counteract the force of the atmosphere, the pressure of the atmosphere, and so you can get the pressure of the gas as the pressure of the atmosphere minus the line of mercury. Now, if you have a gas with a pressure that is higher than the atmosphere, then the atmospheric pressure plus the height of the mercury will have to counteract the pressure of the gas, and therefore the pressure of the gas equals the atmospheric pressure plus this H that you can measure. So this way you can measure the pressure of a gas when it's below or above atmospheric pressure. So how can you use that? Well, one of the first quantitative laws concerning gases was Boyle's law, which related the pressure and the volume of a gas when the temperature is kept constant. Okay, and so you took a certain amount of a gas, kept the temperature constant, and then he measured what is the relationship. If you change the volume of the gas, how does the pressure change? So what can we do? Well, what we do is set a certain volume. Okay, very importantly, we don't let any of the gas out, right? So this is the amount of gas we have. And so if the volume was 48 cubic inches, then you measure the pressure and find it to be 29.1. Then you decrease the volume, okay, possibly by, well, we'll see certain setups, but you can just, for example, push it to a smaller volume with a piston. You measure the pressure again, and then another volume, another pressure. So you build this volume pressure pairs, and then what he found was that if he multiplied the volume by the pressure, then he always got the same number. So you can see here that the first pair gives you this number, 14.0, 14.1, 14.1, 14.0, 14.1. And so it seems like the pressure times the volume of a gas is a constant. Okay, and that constant, of course, depends on the temperature, but if the temperature is kept constant, then the pressure times the volume is always constant. So one way to do that, and then we can even do it in the lab, is you start out in this state, right? So you can measure the volume of a gas, right? It's a tube, right? So you know the inside diameter of the tube, then square that times pi, and divided by 4, whatever, and then multiply it with the length. So the volume of the gas here is going to be proportional to the length. And so you can measure the pressure by, the atmospheric pressure plus the height of mercury, and the volume. Now, if you add the little mercury in here, then it means that you can increase the pressure, the volume decreased, and now you can measure the new volume of the gas here, and then the new pressure, okay, by the length of the mercury. And so this is a simple way to carry out this experiment. And if you plot it, and then you see on the x-axis you have the volume, and on the y-axis you have the pressure, and then you get this reciprocal relationship. What does it mean? That, for example, if you have this point here, okay, and then if you increase the volume by a factor of 2, then the pressure from here to there will drop by a factor of 2. Okay, and so this just means that the pressure times the volume is a constant, or you can say that the pressure is proportional to 1 over volume. Okay, so the pressure is proportional to 1 over volume, or vice versa. And so if you plot the 1 over pressure on the x-axis and then the volume on the y-axis, then you get a straight line, and then the slope is some sort of a constant. Okay, so now we know how the pressure and the volume are related, and let's introduce right away the concept of an ideal gas. So what is an ideal gas? Well, ideal versus real. Okay, so in an ideal course, the professor teaches you everything. The exams are only about the material. They're not too complicated, and then you get an A, right? And all the students, of course, are very committed. Now, in a real class, it's not always so. So what's the difference between an ideal gas and then the real gas? A gas that obeys Boyle's law is called ideal. In a real gas, it may deviate somewhat, but you can see that actually this is very little deviation. You can see that if you compare neon to O2 to CO2, and CO2 is a large molecule, right? Then you can see that even though the ideal gas will always have this same constant for the pressure times the volume, no matter what the pressure is. For a real gas, it slightly deviates, but very slightly, right? I mean, helium is actually very close. O2 is very close. For this entire range of 1 atmosphere, it only deviated by this much. And even CO2 is, instead of a 2.4, 1, it gives you 2.26, okay, at an atmospheric pressure. And so, so this means that in fact the gases, for the most part, behave somewhat ideally. Neon is more ideal than oxygen, and oxygen is a much more ideal behavior than CO2. Okay. The next law that we will discuss is, so what other properties are there for a gas? Well, we have the pressure and the volume, and of course the next one would be the temperature, right? This guy, Gay Lussac, he was actually quite a fun person. He did a lot of work on gases. He was the first guy to fill a hydrogen balloon, right? Which sounded like a good idea until the Hindenburg, right? And he made the first solo balloon fight. So I guess he liked adventure and wild things. And he determined that the volume of a gas increases linearly with the temperature, right? And I intentionally didn't say proportionally, and then we'll see what the difference is. So if you plot the volume of a gas as a function of the temperature, and then since he was European, he measured it in Celsius versus the volume of a gas, then you get these straight lines, right? So this is a straight line for helium, for methane, for water. You can see that, and let me blow this up, right? So you can see that after this point, the curve for water, or the line for water, becomes dotted, and for N2O, it becomes dotted here. And then for methane, around the minus 90 degrees. Why is that? Well, the reason is that at that temperature, the gases will condense, right? So we cannot talk about a gas anymore. But for helium, you can extrapolate down all the way down to almost zero volume. So what does it mean? Well, the interesting thing about all these lines is that they all extrapolate to the same point, right? This is the point where every gas will collapse to zero volume, okay? In some cases, that's a huge extrapolation from water from 100 Celsius, right? And that temperature is found to be minus 273.15 Celsius. So it seems like you cannot go lower than that temperature, right? Because at that temperature already the volume is zero. And so we can call this the absolute zero temperature. And then we can build a scale, a new temperature unit that will have its zero there, and then measure the temperature relative to that. So what does the Charles law say? That if the temperature is measured in a unit that starts from the absolute zero, then the volume is simply proportional to the temperature. If you raise the temperature again in a unit that starts with absolute zero to twice the temperature, then the volume will double as well. We can very nicely illustrate this by, let's say, taking a balloon. Okay, you can see the balloon has a fairly large volume, and then if you start cooling it down, then that volume collapses to something very, very small, and so the volume decreases as the temperature decreases, right? So the temperature goes down, and then the volume went down as well. Okay, what's next? Well, we have a certain amount of a gas, right? And then we can we have established relationship between the pressure and then the volume and now the temperature. But what about the amount of the gas that is in there? And then we've already mentioned this. Remember when we talked about atomic theory, and then we talked about the atomic masses and how historically they were determined. And then one of the key pieces was Avogadro's law. Okay, so Avogadro's law says that equal volumes of any gas at the same temperature, and that's important, and pressure contain the same number of particles, which means that the volume is proportional to the number of particles, or for us, since we count them in moles to the number of moles, right? So the volume is proportional to the number of moles for any gas, okay? And this is very important because now we have 4 quantities that we have the relationship in between. We have the pressure, we have the volume, we have the temperature, and we have the number of moles. Then we have the relationship between any of these, right? We have the relationship first between pressure and volume, and then with the temperature, and now the mole as well. So we can put these two together. We can take the 3 individual gas laws. Okay, so how does it work? Well, first we determine that the pressure times the volume is a constant if the temperature and the number of moles were constant. So that was Boyle's law. Then we determined that the volume is proportional to the temperature and the volume is also proportional to the number of moles. So if you put it all together, then you get one giant gas law. And then this is the one that's going to form this very center of this chapter, that the P times V equals nRT. So the pressure times the volume equals the number of moles times the temperature. And then we have to put in a constant, right? I mean, these 3 laws each had their own constant. And then we just put these 3 constants together, and then we call this the gas constant, and this is typically denoted with an R. And then what would be the unit? So if you experimentally measure it, then in SI you get 8.314 joule per mole Kelvin. Now why is it joule per mole Kelvin? Well, for that let me open a blank screen. So let's start with this PV equals nRT and express the R from it, right? So the R equals PV over NT. And so therefore the unit for the R has to be the unit for pressure times volume divided by N times T. So what are the units here? So the pressure is measured, and then I'll do the simple one first, in atmospheres. Okay, the volume can be measured in liters, and this is what the book will do for the most part, and then divide it with mole, and then a unit of temperature that starts at absolute 0. We call that the Kelvin, right? And so liter atmosphere over mole Kelvin is a good unit for the R. Now, what if we want to do SI? And that's a little bit more complicated. So what will be the unit of pressure times volume, right? So the pressure is measured in pascals in the SI. The volume is measured in cubic meters. And so do we want to call it Pascal cubic meter over mole Kelvin? Well, luckily not. And that's the power of the SI system. So what's the Pascal? Pascal is Newton over square meter, and then the square meter will cancel out a lot from the cubic meter, but let's not do that yet, because what is the Newton, right? Newton is force, and then force is mass times acceleration. Okay, so let's do that. Kilogram, what's the unit for acceleration? A meter over second square, but we already had a meter square, and so this meters canceled out, and then we have kilogram over meter second square. And then if you put that in here, then this becomes kilogram. Let's try to not lose anything, times meter square over second square. And then if you recognize this, you can also write it out as kilogram times meter over second square. So then this becomes the Newton, and then this is a meter, so Newton meter. Remember Newton meter? That's force times distance, so that's the energy unit. So this is called the joule. Okay, so now we have an SI unit for it, and let me put it in here, and that's joule over mole times Kelvin. Okay, let's close this. So that is why the SI unit for the universal gas constant is joule over mole Kelvin. And then the book and then several American textbooks use liter atmosphere over mole Kelvin, and you have to memorize, unfortunately, this value in order to do this calculation. And you can memorize either one. I actually usually memorize this one because that has a wider use when we go to the thermodynamics chapter. Then that's going to be very useful there. But if you just want to use a calculation between liter atmospheres, then you can use this. And then how far do you have to memorize it? I would recommend knowing it about that many units, right? So that would be a liter atmosphere over mole Kelvin. And then very importantly, we call this the ideal gas law. What does it mean? That gases that we consider ideal obey these laws, right? And so a gas that obeys this law is considered an ideal gas, okay? And for a real gas, it will deviate from this law, and then we'll learn about what conditions it is closest to the ideality. Now, again, this concept will come up in a later chapter, but for now, you can also express this law instead of measuring the number of gas molecules it's a very large dozen, right? The mole, you can measure it one by one. And so if you put in the number of particles instead of number of moles, then you'll have a different version of the gas constant, and we'll call it Boltzmann's constant. And Boltzmann's constant is related to the ideal gas constant by the Avogadro's number, right? And so Kb is simply R divided by Avogadro's constant. So it's roughly about 1.38 times 10 to the negative 23. What would be the unit? The joule per Kelvin in that case, right? Because we don't have mole anymore. All right, very good. So we have this PV equals nRT, and then the rest of the chapter is going to be centered around it. But first, let's do a few problems with it. Okay, so what kind of problems can we do with the PV equals nRT? Let's start with the first one, that we have a hydrogen gas sample, and then the volume is 8.5 liters, the temperature is 0 Celsius, and then the pressure is 0.2 bars. How many moles of H2 will be in this sample? Let's open a blank screen and start out with PV equals nRT. And then what we're looking for is the N, right? So the number of moles is PV over RT. Then we just put everything in here. The pressure is set to be 0.20 bar. The volume is 8.5 liters. And then right away we'll see what is the temperature was set to be 0 Celsius. So what if you put it in here 0 Celsius? Well, then you're dividing with 0. So that shows right away that Celsius cannot be used. Now worse than that, what if you put it in let's say as a negative Celsius? Let's say the question is at minus 10 Celsius. Then you would get a negative number, right? How can you get a negative number of moles? Of course you cannot. So you would have to convert it to Kelvin. And so let's put first in, what would be the right kind of an R to use in this problem? Well, we have bar, right? So the bar is neither an atmosphere nor our favorite SI unit Pascal. So we can put that in as 0.20 times 10 to the 5th Pascal, right? Because 1 bar is 10 to the 5th Pascal. And then what about the liters here? Well, 1 liter is 10 to the negative 3 cubic meters. Why is that? Well, remember, first time we talked about liters when we introduced concentrations, right? A liter is the volume of a cube, which has a side that is 0.1 meter in length, or 1 decimeter in length, or 10 centimeters in length. And therefore, this 8.5 liter is 8.5 times 10 to the negative 3 cubic meters. Okay, then we can put the R in the SI unit, 314 joule per mole Kelvin. And then right away and then you can see that the Kelvin needs to be canceled out with Kelvin, and so you put it in as 273.15 Kelvin. Okay, and if you put it all in like that, so the pressure 0.2 times 10 to the 5th Pascal, the volume is 8.5 times 10 to negative 3 cubic meters, and then the rest as written. Then let me calculate it for you. 0.2 times 10 to the 5th times 8.5 times 10 to the negative 3 divided by 8.314. I usually memorize it to 4-digit. The next digit would, I think, be a 5 if you really wanted to do that. 273.15 kelvins, and you get 0.075, because most of these numbers were given to two significant figures. What is the unit? Well, everything else cancels out, so we're left with moles. Okay, just a side step here, because while everything was given to two sig figs, what about the temperature? So how many sig figs are there when I say the temperature is 15 Celsius? Well, you look at it and you say, wow, this is two significant figures. But remember that any calculation about a gas is done in kelvins. And so you have to look at the number of sig figs in kelvins as well. So when you add that 273.15, right, then you see that this is going to be 288.15 Kelvin. And then where's the last significant figure? Well, the last significant figure is the last significant figure of the 15. So it's this. So how many sig figs is that? Now it's suddenly 3 sig figs. So just remember that when I'm talking about the sig figs for the temperature in a gas law, then I mean it in Kelvin. And so an even more extreme example would be, what about 1.5 Celsius? Well, you put it together, then you have to add it to 273.15, and you get 274.65, right? 274.65, in which this is the last significant figure. So this 1.5 is not 2 sig figs, actually 4 sig figs in the calculation. Okay, very good. So that was the first problem. Second problem is, what if we have a sample of ammonia and the volume is 1.5 liters, the pressure is 1.37 atmospheres, and then we compress the volume to 1.25 liters. The temperature is kept constant. So if the temperature is kept constant, then we're down to the Boyle's law, right? What with the final pressure? So in this case, we don't have to use the machinery of the whole PV equals nRT. We can just state that the P times V is constant. So the pressure before times the volume before equals the pressure after times the volume after. And so the numbers were, I believe, first pressure was 1.37 atmospheres, and then the volume was 1.5 liters, and that equals the final pressure that we're looking for, and then it was compressed to 1.25 liters. So how can we do that? Well, we just have to divide over with 1.25, and so the new pressure is 1.37 times 1.5 divided by 1.25, which happens to be 1.644 atmospheres. And then how many sig figs do I have? Well, the number with the smallest number of sig figs is 1.5 liters, so I only have 2 sig figs, so that's 1.6 atmospheres. Okay, now what unit do I have to use? Well, it doesn't matter. Whatever unit we have for the pressure on one side, that's the unit we will have on the other side, as long as the volume is given in the same units on the two sides. Okay, so that makes it very, very simple. So that's pretty much it. Okay, let's go back. And then there were a few more problems here. Okay, so we've done this. Now, next one, we have a sample of methane gas, and the volume is 2.8 liters at a temperature of 15 Celsius, and you heat it to 75 Celsius, what would be the new volume of the gas? Well, you can see that the pressure is constant, right? It said that the pressure is constant, which means that we can just use Charles' law, right? What did it say? Well, if we forgot, we never forget the PV equals nRT, right? And then in this problem, we said that the pressure is constant, right? The number of moles is constant because it's the same, right? It's we didn't pump in new gas. It's a sample of a certain gas. The R is a constant, and therefore the volume is proportional to the temperature, right? So you can also say the volume before over the temperature before equals volume after over the temperature after, right? So by simply dividing with the temperature. Well, this is not a good division, whatever. Okay, so let's just put in the numbers. And what we're looking for is a new volume. So the volume was 2.8 liters and the temperature was 15 Celsius. So do I put it in 15 Celsius? Obviously not, right? 15 Celsius had to be converted to kelvins. How do I do that? I had 273.15, and so that becomes 288.15 kelvins. Okay, this was before, and then the new volume is what we're looking for. We keep it as a V2, and then as I see, the temperature is 75 Celsius, so that will be 348.15 Kelvin. I hope I did it right, and I probably did. So what would you get for the V2? We'll just multiply over the 348.15. So let's see, 2.8 divided by 288.15 and multiply by 348.15. I get 3.383. How many sig figs? Well, I had the original liter given as 2.8, right? The original volume 2.8 liters. So this is 2 sig figs. How many sig figs was the 15 Celsius temperature? It was given as 15 Celsius. But again, 15 Celsius, how many sig figs? Actually 3. Remember when you convert it to kelvins. But still, the volume with the 2 sig figs is what determines it. So it's 3.4 liters. All right, very nice. Let's go back to, so we did the third one. And now let's see a bit more complicated one. So we start out with a certain pressure and temperature and volume. And then we change 2 parameters. We change both the temperature and then also the pressure. And then we ask for what's the new volume. So we'd have to use either P equals nRT, calculate the N and recalculate everything, or better, let's just derive an alternate form of this. So PV equals nRT, right? So this is what we have memorized for life now. And let's divide over with the temperature. So the PV over T, the 3 important parameters of a gas, some certain sample of gas equals N and R. And then the N was constant, right? It's still the same sample of gas. And then the R is universal Gauss constant. So that's definitely a constant. And so we can say that this is constant. And so what I can say is the P1 V1 over T1 equals P2 V2 over T2. And this is the formula that I have to use. And the rest is easy peasy. Let's just put in all the numbers. 350 torrs times the original volume was 2.54 liters. And the original temperature was minus 25 Celsius. So that would be 248.15. I hope, Kelvin, and that's equal to, what's this asking for? It's asking for the new volume. So the pressure is now 750 torrs, and it's framed as compressed to this pressure, right? Remember, when you're decreasing the volume of a gas, that's what compression means, then the pressure increases, right? So 750 torrs, the new volume is what we're looking for, the V2, and then we said that at the same time, the temperature raised to 10 Celsius, and 10 Celsius is 283.15 kelvins. Okay, so it doesn't seem very difficult, right? You just put in more numbers. So 350 times 2.54 divided by 248.15 multiplied by 283.15 and divided by 750, and that gives you 1.35. How many sig figs? Well, this is 3 sig figs. This was given to a whole Celsius, so this is 3 sig figs, but the torr here and the torr there, remember that the trailing zero is only significant if there's a decimal point in there, so this is actually only 2 sig figs, and this is the last significant figure, so I have to round it to 2 sig figs. How do you round from a 5? Well, you have to check the next digit, and then this says 1.3525, and so I have to round it up, so it's 1.4 liters. Okay. And if the 350 and the 750 were given as 350 dot torrs, then I would say 1.35 liters. That's the answer. Okay, very nice. Well, let's put the check mark here too. So what were these problems like? The first one was a PV equals nRT problem. The second one was a PV equals PV problem. Then this one was a V over T equals V over T problem. And this is a PV over T equals PV over T problem. Okay. But again, any of them could be rephrased into the PV equals nRT. Now, one more thing that is kind of interesting here, and that is how to get the molar mass from the density and vice versa. Well, the density of a gas is simply, or density of anything, and that is the mass divided by the volume. Now, how do you get the mass? Well, if you know the moles and the molar mass, then it's the moles times the molar mass. Remember, molar mass is expressed as grams per mole, and so multiplied with mole, you get the grams. So the mass is number of moles times the molar mass, the volume stays, and then you have something that looks like an N over V. How can you convert that? Well, let's look at it. PV equals nRT, and then I rearrange it so that I get the N over V on the right side. So I have divided over volume. Let's remove the RT, so divide over with that. So P over RT equals N over V. And so instead of the N over V, we put in the pressure over RT here, right? Then we get a formula for the density. And so if you want the density from the molar mass, so it's molar mass times pressure divided by RT, or you can get the molar mass from the density. If you measure the density of a gas, it's RT over P. Okay, so what does this mean? This means that if you know the molar mass of a gas, you get its density. And it also means that the density is actually proportional to the molar mass. And so if you go from a gas with, let's say, an average molar mass of 29, what would that gas be? Well, that's air, right? Because air is roughly 3/4 nitrogen, 1/4 oxygen. And nitrogen is 28, oxygen is 32, so you get around 29. So air is approximately 29 grams per mole. Okay, and you go to something, let's say CO2 is 44. That means that CO2 is a lot heavier, right? The density is proportional to the molar mass, and if the molar mass is 50% higher, like the 44 versus the 29, then it means that the density is 50% higher as well. And so that is why if you have a room, right, and then you have CO2 in air, then the CO2 is mostly down here. Okay, now does it make it more or less dangerous? Well, it depends on if you're unconscious lying on the floor or not. But what about CO? So carbon monoxide, that is roughly at 28. And 28 is very, very close to 29, which means that the CO, carbon monoxide, does not sink down to the bottom, but it's everywhere. You have CO here, you have CO here, and so you have CO there. And that's why carbon monoxide, which is actually very toxic, is more dangerous, a lot more dangerous than carbon dioxide. It's because it's everywhere. And so if you have, let's say, a bad furnace, which doesn't burn to CO2, but burns to carbon monoxide, then the carbon monoxide gets everywhere and you breathe it and then you die. And that's why I think in California, it's actually mandated to have a carbon monoxide detector nowadays. Okay. So, that's it. So just the take-home message is the density is proportional to the molar mass. How can we use this PV equals nRT as a real chemist, right? And then do stoichiometry, right? Stoichiometry is something that we really want to do. And in stoichiometry, we carry out the calculation in moles, right? So how can we get moles? Well, we've seen the stoichiometry problem so far. How did they look? Well, typically you start out with grams of something, convert to moles of something, convert to moles of something else, and then you convert it back to grams. And so these are the conversions that you typically do, and then you use the molar mass. And so to convert between the moles and the mass, you need the molar mass. So to convert between moles and volume, you use the molar volume. So what is this molar volume? Well, interestingly, of course, since the PV equals nRT applies to any ideal gas, not just one particular gas like the molar mass, then we can just use the PV equals nRT and it will be the valid number for any of the gases. And so what would be the volume of 1 mole gas at standard temperature and pressure? And the standard temperature and pressure, of course, is a matter of definition. And then this book uses, and a lot of other textbooks in the US, they use 0 Celsius and then 1 atmosphere as the temperature and pressure what we want to calculate when we do the calculations. And this is what this is the number that we want to memorize for the volume. And if you put that into the PV equals nRT and calculate what is the volume of 1 mole of a gas, well, you just have to put in 1 mole for the moles. Then you put in the R as usual. You put in the standard temperature, and then you put in here the standard pressure, which is 1 atmosphere. Now you can do it in the liter atmosphere and mole Kelvin way, or I actually chose to do it in SI. It's actually a good idea to get used to the SI as soon as possible. And if I put everything in, I get a number that is 22.414 liters for 1 mole of a gas. And so if I want to express it as a molar volume, then it will be 22.414 liters per mole. And again, liters of moles of what? Anything, right? Anything that behaves ideally, any gas that behaves ideally becomes the same number of 22.41. Now, by the way, if you look at other STPs, in fact, the STP entry in the Wikipedia is kind of fascinating because depending on the country, depending on the use, like engineers use again a different one, then you get various STP definitions. So another STP definition, which is much more widely used in thermodynamics internationally, and that would be a room temperature, which is the standard temperature at 25 Celsius or 298.15 Kelvins. And then the standard pressure is typically a bar, which is almost like an atmosphere, but remember, bar is 10 to the 5th pascals. And so there, the molar volume is approximately 24.8 liters, very close to 25 liters. So you can say that at room temperature and around atmospheric pressure, you have 1 mole of a gas in about 25 liters. That's actually good to keep in mind, because if you do any gas stoichiometry problems and you get a number, then you should have a feel for it, right? So, I mean, what does it mean? Did I get the right number or not? And so it's good to remember that approximately a mole of gas is about 25 liters. at room temperature. Now let's see a problem. So we have calcium carbonate, and it says decompose, thermal decomposition. So it goes to calcium oxide plus CO2. And the CO2 is the gas we're talking about. So what volume of CO2 will be produced at STP from the decomposition of 160 grams of calcium carbonate? Again, there's not enough room on this slide, so this is what we would be doing on the whiteboard. I already kind of forgot the numbers. So we start out with 160 grams of calcium carbonate. Okay. Then you want to convert it to moles of calcium carbonate. So 1 mole of calcium carbonate is how many grams of calcium carbonate? Well, we would need a periodic table for that. And so let's see. Find it in a moment. Okay, so, well, actually I'm kind of cheating and I just use a database. So it's 100.0869. 100.0869 grams calcium carbonate. Right, so now I have moles of calcium carbonate, and the question was the volume at STP. So I just put in the molar volume, and so I have converted to moles now, and the molar volume is 22.414 liters per mole. Mole cancels out the mole, so I'm stuck with liters of, I forgot how do I undo this? I forgot to, I honestly don't know. So let's do the following. I put in the eraser. Haha. Okay, so first, let's do it step by step. Let's not skip a step here. And then I go back to, it works. Okay, so let's first convert this thing to CO2, right? So I'm interested in the CO2. So 1 mole of CO2 I get from 1 mole of calcium carbonate. You saw the balanced equation before. And now we can put in the 22.414 liters per mole. And now I have moles of CO2 canceling each other out, and so I left with liters of CO2. So if I put this together, I get 160 divided by 100.0869, if I can read my own handwriting, times 22.414, and then I get 37.18 liters of CO2. How many sig figs did I start with? Well, I said 160 grams, so that's 2 sig figs, right? So then in the end, I get 37 liters of CO2. Now, does it make sense? Well, I told you that about a mole is about 25 liters. And then since the molar mass was 100 grams, and then I get 160, so I got about a mole and a half, and a mole and a half is approximately 37 liters. So all good. Okay, now, so we've done that. Now, a very important point here is going to be, how does a gas look like? Okay, so first of all, I told you that, the molar volume is independent of what kind of a gas. The whole PV equals nRT is independent of the kind of gas. I told you that gas molecules, gases, they all behave the same. If they're ideal, and then we'll see when they become most ideal. Ideal means that any gas behaves the same way, and that same way is the PV equals nRT. So can you imagine when you take 2 different kind of gases and then you mix them, right? If it doesn't matter what kind of a molecule is flying around in a gas, then it wouldn't matter if they're not even the same kind. So if you take a mixture of 2 gases and put them together, they should behave exactly the same way as the pure gases would. Okay. Furthermore, you can also imagine that, I have, let's say, 1 mole of helium. And I work out the PV equals nRT from the N. I get the pressure in a given volume. What if the N is now still 1 mole, but now it's half a mole of helium and half a mole of argon? And then when I put it in there, I could get a PV equals nRT for the helium, and I get a PV equals nRT for the argon. And if I add it together, then I simply added the pressure coming from the helium molecules hitting the walls, helium atoms, they're monatomic, right? And then the argon atoms hitting the walls, and I added the pressure. That's the total pressure we get. And so that leads us to talking about mixtures of gases and the concept of a partial pressure. So a partial pressure, why is it called partial? Is because it's not the total pressure that the gas mixture extends, but it's the pressure that is due to one component of a multi-component gas, that is, of a mixture of a gas. And so the Dalton's law of partial pressure, which dates back, 200 years ago, is that the total pressure is going to be the sum of the pressures coming from the individual components. So for a mixture of gas in a container, the total pressure exerted is the sum of the pressures that each gas would independently exert if it was alone in the container. And so how does that work? Well, the total pressure is the pressure of one gas, and then the P1 is simply, the volume is the same, right? They're all in the same container, right? So this V and this V and this V are the same. And also the temperature is the same, right? Because they're together, right? You cannot imagine that you have a gas of mixture and then one component has a higher temperature than the others, right? And so temperature and temperature are the same. And so I have an individual PV equals nRT for component 1, component 2, and component 3. And then when I add them up, what I get is that the RT over V is the same, so I can bring the number of moles to the front, and then they add up, and then this is the sum of the moles, or the total number of moles. And so what I get was that the P total equals V total times RT over V, so I get the PV equals nRT for the whole mixture. So I can write an individual PV equals nRT for any of the components, and they all add up to the PV equals nRT for the sum of the moles and the sum of the partial pressures, which is total pressure. Okay, very nice. So how can we use this? Well, first, what does this tell us, right, before we do any calculations? So this means that the pressure exerted by an ideal gas does not depend on the composition. It just means how many gas molecules you have, independent of what kind they are. So if you visualize this by 4 blue molecules exert this many pressure, let's say 2 whatever units, and then you have 10 gas molecules of a different kind, then the pressure would be 5. If you add them up, then now you have a total of 14 whatever unit of gas mixture you have, and then the pressure is going to be the sum of the pressures, and if you count it, indeed it's 2 plus 5 equals 7. Okay, what does it tell us? Well, it tells us that 2 things are unimportant about the gas. First of all, the volume of the individual gas particle is not important, right? Because you can imagine that, let's say, a neon atom is much smaller than, let's say, CO2, okay, triatomic. Or you can imagine that also the forces between the gas particles is not important, right? If it doesn't matter what mixture it is, then it cannot matter that when the particles fly by each other, what kind of an interaction is there in between. And so this means that the forces between the gas molecules at reasonable pressures are very weak, and then the size of the particles is very small. So you can imagine that a gas is really just a bunch of little dots with no volume flying around, hitting the walls, then bouncing back, no interaction between them, and the only thing that they're doing is hitting the walls and exerting pressure on it. And we'll come back to that point in probably about a minute and a half. But before that, let's just connect this Dalton's law of partial pressures to the moles. Remember that the PV equals nRT added up to the sum of the pressure and then the sum of the moles. And so this means that each gas exerts a pressure that is proportional to the number of moles of it out of the whole. And so if you introduce the mole fraction, which we usually denote with an X, and that is the number of the moles of one component over the total number of moles, or N1 over the sum of all the N's. And then you can express this from the ideal gas law for both the individual gas, P1 times V over R, and then the total pressure that will be for all the gases together. Then you can establish that the mole ratio, the mole fraction, is proportional to the pressure, the partial pressure of the gas over the total pressure. And so you can get the partial pressure of a gas as the mole fraction times the total pressure, right? Because simply the pressure, the partial pressures add up as the moles add up. And one particular use for this would be if, and then we often talk about the partial pressure of water, right? You know that in the air there's always some water, right? It evaporates from whatever source you have, and then how much evaporates depends on the temperature. And we'll come back to this a little bit when we talk about equilibria as well, and then also come back to this when we talk about thermodynamics later. But long story short, when you want to collect a gas, right, say you have a stoichiometry experiment, and then here you have potassium chlorate, and if you heat it up, it gives off O2. But you remember when you have a gaseous product and you want to collect it, you cannot just collect it in air, right, because it would diffuse away. So what you do is first fill up a container with water underneath, upside down, and then bubble the gas in it, and then you will fill it up, in this case with O2. But at the same time, when these bubbles go through the water, then water vapor will evaporate into it, and then it will reach an equilibrium. And so then when I say that we collected oxygen, we didn't really just collect oxygen, we collected oxygen and water vapor together. And so to calculate that, I can say that the first one is just too simple, right? How would we do that? Well, remember that the partial pressure is mole fraction times the total pressure. So you take the total pressure, multiply it with the mole fraction, you're good. Okay, so that's for babies. But let's say a more interesting one. So we take a sample of potassium chlorate, and then we form O2 gas, and then we collect that oxygen in water at the temperature of 25 Celsius, and then the total pressure is 1 bar. Then the total volume we collected with 250 milliliters, and the water vapor pressure was 21 torrs. What is the mass of the potassium chlorate that gave us this much oxygen? Okay, so this sounds like a more interesting problem, doesn't it? Come on. All right, there you go. So I kind of need the numbers, right? And so we want to convert back the amount of the oxygen into the amount of potassium chlorate. So the numbers were that the total pressure was 1.00 bars, and the pressure of the water was 21 torrs, okay? And the total volume was 250 milliliters. Let's write it down as 0.250 liters. And the temperature was 22 Celsius, so that's 295.15 Kelvin. Okay, what else? Was there anything else? No. And then the equation read, just so that we're all on the same page, potassium chlorate goes to potassium chloride plus O2, and let's balance together. You can see that we have 3 oxygens on the left, and so it needs to be an odd number there, and I have to multiply it by 2 and 2. Okay, so from 2 moles of potassium chloride, I should get 3 moles of O2. Now, of course, the tricky part is that from these two, the pressure of the oxygen is going to be the 1.00 bars minus the 21 torrs. Okay, so that's an ugly conversion. So how would we do that? Well, let's say I want to do this whole thing now in SI, because most of the stuff I have in SI. So the 1.00 bar converts to pascals as 1 bar is 10 to the 5th pascals, okay, minus the 21 torr, and I don't, of course, remember all the conversion factors, so I can do it stepwise. I know that 760 torrs is 1 atmosphere, but I want it in pascals. But of course, I know that 1 atmosphere is 101,325 pascals. Okay, and if I do that, then that gives me the pressure, right, of the O2 as so 10 to the 5 minus 21 divided by 760 times 101,325. So that will be 97,200 pascals. So how many sigmas do you round this to? You don't. Okay, don't forget that when you have an intermediate calculation, never round it. Okay, don't round. But now I have the pressure in pascals, and I have the volume, and I have the temperature. And then, by the way, if I want to go as fully SI, then this is 2.5 times 10 to the negative 1 liters, which will be 2.5 times 10 to the negative 4 cubic meter, right? Remember, using the conversion factor of 1,000 between cubic meter and liters. And now I have everything, and so the number of moles for the oxygen can be calculated as PV over RT. And let's just put everything in. So the pressure is 97,200 pascal times the volume is 2.5 times 10 to the negative 4 cubic meters, 8.314 joule per mole Kelvin, and the temperature is 295.15 Kelvin. Okay, let's do this. So 90, okay, times 2.5 times 10 to the negative 4, 8.314, and then 95.15. And that happens to be 0.0099 moles of O2. Okay, but the question was the moles of the potassium chlorate, or rather the grams of potassium chlorate, even words, right? So start out with 0.0099 moles of O2 multiplied by the conversion. So I have 3 moles of O2 here, right? From 2 moles of potassium chlorate. And then I want it in grams, right? So 1 mole of potassium chlorate is how many grams? Potassium chlorate. Well, let's look it up again. Okay. And let's find the molar mass. Okay, potassium chlorate has a molar mass of 122.55. 122.55 grams of potassium chlorate. And so I take this number again. I didn't round it. I just took it from the calculator as I obtained it, 122.55, and that gives me 0.81. How many sig figs did I have in this problem? For the most part, so I had 3 sig figs in the bar, but only 2 sig figs in the volume, and 2 sig figs. Well, no, that doesn't matter. So I have 2 sig figs in the end, so that's 0.81 grams of potassium chlorate. And then I can. Okay, I hope I haven't made a huge mistake here. And then the end, it will be 0.81 grams of potassium chlorate. Again, how did I do it? Well, the important part for, the Dalton is to take the total pressure under which we collected the gas and then subtract the pressure, the partial pressure of the water. And then the subtraction was kind of tricky because it was different units. So I subtracted torr from a bar, and so you converted both of them to Pascal, did the subtraction, and put that Pascal into the PV equals nRT. All right. Now, we're done with this. So remember what I said about the significance of the Dalton's law of partial pressures. It seems like the volume in the individual particle is small and then the forces are negligible. Okay, this means that I can imagine that a gas is nothing more than just a bunch of dumb dots that are flying around with a mass and hitting a wall, exerting pressure while they don't influence each other. And now we will be talking about gases from a different perspective. Remember when we started out, all these gas laws, Boyle's law, Charles' law, Avogadro's law, they were based on measurements. They were based on experiments, right? We measure the volume of a gas, the pressure of a gas, establish these relationships. And we arrived at PV equals nRT, and then the R was also obtained from experiments, right? We do measurements on real gases and tried to measure them in the most ideal conditions, and that gave us these equations and then this constant. But what about the physics? What's the underlying reason that gases behave this way? And so that leads us to this kinetic theory of gases. And what we'll do is we'll just make a few basic assumptions and then try to derive the equations from elemental physics on what the gas molecules, how the gas molecules should behave. And so our assumptions to derive this will be, first, that the particles are very small compared to the distances, right? We've seen this before, that it doesn't matter what kind of particle it is according to Dalton's law of partial pressure, and so it means that the volume cannot matter, and so the volume of the individual particles is zero. Okay, now, next thing, where does pressure come from? Well, pressure comes from the collision of the particles with the wall, right? So the particles with a mass but no volume, they just hit the wall, they exert pressure, and then bounce back. Now, importantly, particles don't attract or repel each other, so they just fly by. They may collide with each other, but it doesn't matter because all it does is then the particles will just turn around with the same velocity, okay? And then the next thing is, and this will introduce at the very end, that what is the meaning of the temperature, right? We have an understanding of temperature, right, since we were small, that, there's something that is hot, there's something cold, and then typically temperatures go towards each other. So cold object warms up in a warm room, hot object cools down. But what is the meaning of it? And then one meaning that we'll say is that the average kinetic energy, of a gas. What is kinetic energy? Remember, it's half mv square, where this is the mass here and then the velocity. And so the average kinetic energy of a gas molecule is proportional to its temperature, right? So this is proportional to the temperature, and that's the meaning of temperature. So what we'll do is we'll take a box, and the box has, of course, 3 dimensions. Each length of the side is L, and then we have a particle, and the particle just flies around, hits the wall, bounces back, hits another wall, and so on and so forth. And then we use just elemental physics elementary physics, that is, what are the forces, and then try to add it all up together. So how does it go? Well, first of all, remember that the velocity is a vector. So it has three components in the x, y, and then a z dimension. The total velocity is then, of course, Pythagorean theorem is the sum squares, right? So you take the individual velocity components, square them, and that would give you the total velocity square. Okay, now once we have the velocity in any direction, let's look at the x first. Okay, so in the x direction, you take the velocity, and that would be, right, if you multiply this, then this will be the component. So how often it will hit a wall depends on the size of the box, right, and then the velocity, and you can calculate it as the time will be distance over velocity, or 1 over time is what we call collision frequency. So how many collisions happen in a given amount of time, that would be the velocity divided by the distance, right? And so ux over L is how many collisions we have in a second. Okay, so now that we have the collision frequency calculated here, let's talk about the force, right? What is the force of a collision? Well, force in general is mass times acceleration, right? And then acceleration is the change in velocity over the change in time. And so if we take the mass and put it in here, then this quantity here is the momentum, right? So the change in momentum over time will give you the force. And in one collision, don't forget that the final momentum minus the initial momentum is the change in momentum, and it's twice the momentum. Why? Because it goes in one direction, right, and then turns back and goes in this direction, right? So the net change is the reverse momentum minus the original momentum, so it's twice as much. Okay, and so then the force is going to be this over time, and so the force in the x direction is going to be the change of momentum over time here, and then we calculated that. Now how often does this happen is what we calculated the collision frequency, and when you put the two together, then you get twice the mass times the velocity square in the x direction divided by the length of the box. So this puts together, how often collisions happen, so the 1 over delta t, and then what is the change in the momentum for each of these collisions. And again, it's going to be twice the momentum, right? Because when it hits the wall, then it completely reverses the momentum and comes in the other direction. Now, you can do the same thing with the y and then the z direction, and then you can add it up. The total force is going to be the force acting in the x direction plus the force in the y direction plus the force in the z direction. And then the individual ones are given here. And then you add it up. And remember that the Pythagorean said that the total velocity square equals the individual velocity component squares summed up. And so what we have is 2mu square over L gives you the total force on the box. Very good. Now, what does this mean? Is that the average force, okay, is going to be the average velocity square, right? So the average force is here, and the average velocity square times 2m over L is the force. But of course, we're not interested in the force. We're interested, well, if we're a Jedi, we're interested in the force. But we are interested in the pressure when we talk about the gas. So what is the pressure? Well, the average pressure that a particle exerts is the average force over the area. Now, what is the area here? Well, that's why we chose the box, right? Remember that the box that looks like this, it has 6 sides, right? And then the total area of each of the sides is L squared, and then we have 6 of them, so we have 6L squared for the total area. We just calculated the average force. So now we can put it together, and the 3 comes from, the 2 up here and then 6 up there, so it becomes a 3. We have mu average, mu square average, And now we had one L here and L squared there that adds up to L cubed, which is very nice because L cubed happens to be what? Well, if it's L, L, and then L, then the volume is L cubed, right? And so we can put the volume in here instead. And so what we have is m u square average over 3v. And also, this was for one particle. So the total pressure from all the particles would be how many particles you have, and that is the number of moles of particles times Avogadro's number, obviously, right? So this is how many particles you have. This is the pressure, average pressure exerted by one particle. And when you put this all together, and then also realize that what is this mu square? Well, this is twice the kinetic energy, right? Because the kinetic energy is 1/2 mu square, the average kinetic energy, right? And so that is twice that. And so what we can do is put that 2 out here, and then we arrive to 2/3 number of particles, their average kinetic energy divided by the volume. And if you rearrange it so that you get all the usual suspects on one side, so the PV over N, where have you seen this? Yes, it's the PV equals nRT, right? And so the PV equals N is proportional to 2/3 and Avogadro's number times the average kinetic energy per particle. Now, of course, this together is the average kinetic energy of a mole of a particle, right? And so you can take this and then compare it to the PV equals nRT, right? And how do we do that? Well, remember that the PV was R times T, and if we say that PV over N is proportional to the average kinetic energy, right, and the average kinetic energy is proportional to temperature, then the PV equals N is proportional to the temperature. So, what does it mean? That if the temperature is a measure of the average kinetic energy of the particles, then we recover the PV equals nRT, in which the PV over N is proportional to the temperature. And then, of course, we've seen that the PV equals nRT, so the proportionality factor is this R here. And then if you rearrange it, then you get that the average kinetic energy, right, from here is 3/2, and this is very important, RT over NA coming from the ideal gas law. And then don't forget the R over NA is what we call the Boltzmann's constant, right? And so you can do that, and then you have 3/2 K, well, you can call it KB, whatever, KT. And so the average kinetic energy of a gas particle is proportional temperature and then 3/2 K times the temperature. Now, where does the 3 come from? Well, if you remember and go back, this is how many dimensions we have, right? We have X, Y, and Z, and that's how we ended up with this 3. So we can also say that on average, on each direction, that is each degree of freedom, right, which directions it can go, we have an average of 1/2 KT energy stored, and this is a very, very fundamental result. And so again, the temperature is a measure of the average kinetic energy, and in each dimension we have 1/2 KT, and with the 3 dimensions together we have 3/2 KT stored. Now remember, these are all averages. So let's talk a little bit about how do we average the velocities. Remember that it wasn't the velocity that we averaged. We took the velocity square, and that is what we averaged. And why? Because essentially this is averaging the kinetic energies. And then so one way to average the velocities would be first squaring them, taking the average of the squares, and then take the square root of it. And this is what we call root mean square, right? The square root of the mean of the squares of the velocity. Okay, so the RMS, we just call it RMS, velocity is then going to be for 1 mole is 3/2. KT would be, sorry, for the Na times the average kinetic energy, and then if you rearrange it, then the average velocity square is 3 RT over NA, and then again remember that the R over NA is the K, so 3 KT over M. And also very nicely, the Avogadro's number times the mass is just the molar mass, right? This is how many you have in a mole, and then what is the mass of one particle, then this is the mass of one mole, and you can put it together and then arrive to the conclusion that the average velocity is square root 3 RT over M, and by the average what I mean is the root mean square, kind of an average. Okay, so that again, we're not averaging directly the velocities, but squaring them, averaging them, and then taking the square root of it. And so if we do such a calculation, just to figure out what it is, so it's square root 3 RT over the molar mass is the U RMS. Let's try to do this calculation for the nitrogen molecule. So we put everything in here, so that will be 3 times 8.314 joule per mole Kelvin. Now, the interesting thing in the SI system is if you put everything in an SI, you get the result in SI. So we don't have to worry about, unit cancellation, this and that, which would be kind of tricky here, right? Because we have joules, but in the end, we want meter over second. But if everything is SI, the result is in SI as well. And so the temperature, the room temperature was 298.15 kelvins. And then what is the mass? Well, the mass has to be in SI as well. And so just roughly nitrogen is, shall we look up the actual value? So, and do... the molar mass. Do we have the molar mass somewhere? Yep. It's I have to find a periodic table. It's 14.007, so times 2 is 28.014. Okay, I may be off by a little bit, okay. But that is grams, and I want it in kilograms, so that's 10 to the negative 3 kilograms per mole. Okay, so again, it's so that we can put it in SI. Now let's see if I can pull this off, and for that I would have to find the square root. Okay, so 3 times 8.314 times 298.15 divided by 28.04 times 10 to the negative third, again because it's kilograms. And then what I got was 515, and then I just used the SI unit for velocity because that's what I should get, and so 315 meter over second, and that kind of looks right? So this is 0 Celsius, so it should be a little bit higher, and then the value I got is somewhere here, right? And so indeed the root mean square velocity is in the hundreds of meters, roughly 500 meters per second. For the nitrogen molecule at room temperature. So that makes a perfect example. Now, in general, as you see that each particle has a velocity, and then what we're looking at in the derivation is just the average velocity, again in the root mean square way. But we have faster molecules and we have slower molecules. So if you plot the relative number of O2 molecules with a certain velocity, and then the x-axis is the velocity here, you can see that there's this distribution, that is weird-looking distribution. We have molecules with significantly higher velocity. We have particles all the way down to 0 velocity and anything in between. And we have a most probable velocity here, and we have somewhere an average velocity, and we have a root mean square velocity somewhere. And this distribution is what we call the Boltzmann, or in this case, it's the Maxwell-Boltzmann distribution. And then it has, again, something like, and this is the most important part here, is something of the sort of e to the minus energy over kT, right? And this is the kinetic energy, which is the mu square divided by 2, and then we have the kT there. And so we have this, which we call the Boltzmann factor, and that is multiplied then with u square, and that gives you this distribution, and this is the Maxwell-Boltzmann distribution. This is one of the most fundamental aspects of any physical science. What is the distribution of energies at a given temperature? Now, let's just look at how they see. So what's the difference between temperatures? So if you go from 273 Kelvin, which is 0 Celsius, to 1000 Celsius and to 2000 Celsius, what you can see is two things change. One is the distribution width, right? So this is a narrow distribution, a wider and an even wider distribution. And also it's shifting to the right. And so as you increase the temperature, two things happen. One, you on average have higher kinetic energy, and remember that the average kinetic energy scales proportionally with the temperature, so that is no surprise. But also it's important that not just the average goes up, but also the width of the distribution, because still the distribution only goes down to zero at zero velocities, and so the whole distribution is getting wider. So this is the meaning of the temperature. At higher temperatures, you have a wider distribution of kinetic energies or speeds, and then the average is shifted to higher values. Now, let's compare these averages, because again, we've introduced the root mean square velocity, which again is averaging not the velocities, but the velocity squares, right? And that is the average kinetic energies. Now, which means that before averaging, it multiplies with itself. And so therefore it overweights the higher ones, right? Because the square is, instead of a linear one, it goes up, right? And so the root mean square velocity is going to be higher than the average velocity. The most probable velocity, again, because of the shape, is longer on the right-hand side than on the left-hand side. It means that the average velocity is actually higher than the most probable velocity, right, than the top of the peak. So this is the most probable one. Then this is the average. And then here, because we're squaring first, the root mean square over estimates the higher velocities, and so that is the highest of the three averages. And again, why do we use it? We use it because we want to average the kinetic energies, because that's what proportional temperature. So let's see, this would be 3 RT over m square rooted. The most probable one. How can you get the most probable one? Well, you take the Maxwell-Boltzmann distribution, right? You take this function, and then you take the first derivative with respect to the velocity, if you can do that. If not, your calculator can do it, and then look for the zero derivative, which will be, this point on top of the curve. And so that will be 2 RT over m square rooted. And then the average velocity is you go over the whole, velocity distribution, and then the probability times the velocity, and then sum it up for the whole distribution. And then if you do that, then you get 8 over pi. And remember, pi is approximately 3. So this will be less than 3, but it's going to be more than 2, and that's why the average velocity is in between the most probable velocity and the root mean square velocity. Okay, now we talked a lot about these various velocities. But let's see now, and why did we do this? Why are we interested in velocities? Because interestingly, some properties of a gas are actually proportional or related to the velocity. And then one important thing is, fusion or diffusion, right? So what are the differences between the two? Well, diffusion is the process of the mixing of gases. And the mixing of gases means that if you start out with, let's say, one gas starting from here, HCl, one gas starting from here, ammonia, then they will diffuse towards each other, and then they will mix, right? Now, how fast that happens depends on their molar masses. Remember that the average velocity, and then again, any of the 3 averages is fine at this point, is proportional to 1 over square root of the mass. Okay, so the heavier it is, the slower it moves. Okay, and that's pretty much true for people too. I'm a lot heavier than my little daughter, so she moves a lot faster than I do. And so HCl here is roughly 36.5, ammonia is approximately 17. And so if that was true, then ammonia, and let's do the actual calculation here. So 36.5 divided by 17, it's approximately 2.15. And if I square root this, I get 1.46. So ammonia should move approximately 1.5 times faster than the HCl. And then you can see here that ammonia went all the way to here and then HCl to here. And when they meet, they form this ring of ammonium chloride. Okay, and that would be one of our, our first gas phase acid-base reaction, right? Ammonia, which is the base, accepts a proton from the HCl, which is the acid, and then form ammonium, okay, and then chloride, okay. And then the significance is that this is a gas, but this is a solid, okay, and that's why we see it. And so what you can see is if you put this together, then you'll see the formation of a ring at this point, and then I'll show you a picture of that later. Now, let's go to the next one, and that's a fusion. And then a fusion is if you have an amount of gas here and a small pinhole through which they can escape to vacuum, then the velocity with which will also depend on their the speed, the rate with which they escape will depend on the velocities. Okay, so going back again to the rate of a fusion, or is also related to the fusion. So the rate is proportional to 1 over the square root of the molar mass. And so between two gases, if you take the ratio of the molar masses, square rooted, but it's upside down, right? So remember that gas 1 is here because it's inversely proportional to the square root of the molar mass. And remember, this is coming from the fact that the average velocity scales with square root 1 over the mass, and so the rate of effusion is essentially depending on the velocity of gas, which is of course not terribly surprising. And so here is an actual photo of how this happens. So if you look at this tube, then what you should see is that the distance traveled by the ammonia is roughly 3 to the 2 or 50% higher than the distance that is traveled by the HCl. Why? Because it depends on the ratio of 1 over the other. The molar mass is square rooted. So if you carry out that calculation, then the distance traveled by ammonia versus HCl is going to be square root 36.5 or something, which is approximately 1.5, right? Ammonia for a smaller molecule travels faster than the HCl. Now, how can this be used, right? I mean, obviously this is a very nice demonstration, but this is huge industrial use, and that is in the isotope enrichment. Okay, so isotope enrichment, the main use is to separate the useful 235 isotope from the 238 isotope for uranium. Why do you want to do that? Well, either because you want to use it in a nuclear power plant, and then you need only a few percent of uranium 235, but the problem is that the normal ratio is about 0.7%, right? So if you want to enrich into a few percent, what you can do is infuse take a series of chambers. There's a wall through which the uranium in a gaseous form can infuse through. But what would be uranium in a gaseous form? So you don't want to heat up the metal and then make it into a gas. What you can do very nicely is uranium hexafluoride is a gas. But you can see that fluorine added mass. And so the difference of 3 between the two will only relate to a 0.004 difference in their rate of fusion. So what does it mean? That the 235 isotope of uranium diffuses 0.4% faster than 238. That's a very small difference, right? And so what can you do? Well, you let them through this porous wall, and there will be a slight difference. And then you take the slightly enriched gas and then do it again and then do it again. And so if in each stage you only get a 0.4%, then to reach an enrichment of 3%, you need several hundred stages. So this is not terribly efficient. And so what they do is they do these in centrifuges, right? And the centrifuges spin very, very fast, and so there's a high acceleration gradient. Okay, let's put it that way. And so when you have thousands of these centrifuges spinning, and then each one slightly enriches the uranium-235 or the 238, do it for a long time, and then you get a few percent of uranium-238. Now, 235. Now, if you want to do more, like the Iranians, who of course are trying to build a nuclear bomb, then you need a lot of these centrifuges, right? And so you need these huge underground facilities where they enrich the uranium, and this is an image of how some of these, well, this was an old facility actually, looked like, and then this giant building, and then how to put it into perspective. I mean, there are some small cars somewhere here, right? And so this is a huge plant. This was the uranium enrichment facility in Oak Ridge, Tennessee, which was constructed for the Manhattan Project to build the first bomb. And then this actually provided the uranium for the Hiroshima weapon, the what they called the little boy. I think, was it Hiroshima or Nagasaki? Anyway, so it was the one that provided uranium for the first bomb, and you can see that even for just one bomb, you need a very, very large facility, because each of the individual enrichment steps only increases the proportion by a very small fraction. Now, there's one more thing that is, of course, a lot more theoretical, and let's cover that, and then we switch to real gases, and then wrap up this chapter very soon. So what about collisions, right? Now, when do two particles collide? And so if this is one particle, okay, and then this will be another particle coming, then if they're close enough, which means the distance is more than twice their radii, then they can collide. So for one particle, you can have this volume that would have a 2D diameter, when d is the diameter of one particle, within which if there's another particle, then they will collide. So this is the marginal case where it will collide with this. But if I put a particle here that is farther out than this distance, then the two will not collide. And so the question is, how many molecules are there in this cylinder, right? That is, how many particles are there that we will be colliding with? Okay, so what is the volume of the cylinder? Well, first of all, the volume of the cylinder for within 1 second, how many particles are there? And what will be the cylinder that this particle travels within 1 second is going to be the cross section of the cylinder, which is d squared pi y, because it's 2D, and you know, right? So if this is the cylinder, then this is 2D, right? And therefore the radius is 1D, okay? Times the velocity average, how fast it goes, times the time that we're interested in. So this will be the length, and then this will be the cross section of the cylinder. And then the collision rate will be how many particles there are in this volume, and so that is n over v. And if you put it all together, then what you get is n over v times the particle size square times square root 8 pi RT over m. Now, there's a slight correction to this, is because in this case, all the other particles were stationary, okay, and so we didn't neglected their motion. So what we need to look at is their relative velocity, and the relative velocity, and that's a little bit more advanced physics, is square root 2 times their average velocity. And so if you put that in here instead, then what you will get is 4 n over v times the diameter square of the particles times square root pi RT over m, and that would be how many collisions there are in a second. Now, the inverse of this, 1 over t, would be, since, that would be collisions per second, so 1 over second is the unit. The time between collisions is the reciprocal of this. So if you take the reciprocal of this, which would be now the collision frequency, right, and then how fast a particle travels within this time, then you get the average distance traveled between collisions, and we call that the mean free path. Why is it free path? This is the path that a particle on average will travel between two collisions. And so again, you take the average velocity here, then you had the collision frequency, and then put together, this will give you the lambda, that is the mean free path. And if you carry out such a calculation, that will tell you how far a particle travels between two collisions, and that happens to be actually a very small value, on the order of micrometers at atmospheric pressure. So you can do and carry out this calculation by simply putting in the numbers. And then what would be a typical value for the diameter of the particle? Well, it's usually on the order of a few angstroms. So for a nitrogen, I would probably put in let's say, for the diameter, maybe like 5 times 10 to the negative 10 meters or angstroms, right? And that would take into account, that spinning N2 particle. Okay, now, this was all very interesting, but so far we've been talking about ideal gases, right? Ideal gases that have no interaction between the particles, their volume is infinitely small, and so these two assumptions from one direction gave us the kinetic theory of gases, which was surprisingly very, very similar to the ideal gas law, which was arrived to from experimental measurements. But how are these two assumptions compared to real gases, right? So that there's no interaction between particles, and there's a negligible volume of each of the particles. And so what we can say is that for an ideal gas, PV equals nRT holds. And so if you divide the two sides, you can say that PV over nRT equals 1, right? And then let's call this the compressibility, like how much gas follows the ideal gas law. For an ideal gas, this is 1, and for a non-ideal gas, this value diverges from 1. So let's see how that looks like. And so here on the x-axis, I put the pressure, and then this compressibility factor is on the y-axis. And then for an ideal gas, it will be a 1. And you can see that for a real gas, it deviates from 1. But remember, these are measured in hundreds of atmosphere. So if they all converts to this value of 1, and that, let's say, for nitrogen, even at 100 atmospheres, it only deviates by, let's say, 10 to 15%. Now, how about the temperature? Like, how would you imagine that now the volume of the particles is it does not depend on the temperature, right? So the temperature is not involved. How does this depend on the temperature, the interparticle interactions? Well, let's imagine that I'm a particle and then you are a particle. And then we're both walking somewhere on campus. I'm, let's say, walking towards a chemistry building and you are walking towards the UC. And then we pass each other. And our interaction would be, some polite chit-chat. Now, if we go very slowly, then we have more time for the chit-chat, right? We spend more time in each other's vicinity, right, close to each other, and we can talk. Now, if you both run because you're hungry and you have to go to the UC, and then I have to run to a chemistry lecture, then we pass each other very quickly, and there's no time for meaningful interaction. And that's similar to gas molecules too. And then if you plot this compressibility factor at various temperatures, the higher the temperature, the closer it is to an ideal behavior. The colder it is, the more interaction will change the ideal behavior for a real gas. And so with that, what we can do is we can take some of these assumptions, throw them out of the window, and come up with better ones. The simplest one would be taking into account the volume of the molecules, right? Originally said that the volume of the particle is 0 compared to the distance in between. But why don't we just assign a volume and let's call it B, okay? And then what is the total volume of all the particles themselves is the number of moles times what is the volume of a particle, of 1 mole of particle, and then you subtract this from the total volume, and then what's called the available, right? This will be the available volume, and put that into the PV equals nRT instead. And if you do that, then typical values for this correction, for this B value, are listed here. What is the volume of a particle per mole? And then if you use, what's the volume of if you think there's spheres, right? So it's 4/3 r cube pi. And then if you take this value, so let's say, for example, let's take nitrogen, and it's measured in liters per mole. You convert it to cubic meters per mole, then multiply it with Avogadro's number, then you get it in cubic divided by Avogadro's number, get it per particle, and then you convert it to the radius, and then you get approximately 2.5 times 10 to the negative 10 meters for the radius coming from this. So these are actually very good looking numbers. So these are in the right neighborhood. We say that the radius of the effective radius of a nitrogen molecule is about 2.5 angstroms, which is about, what we expect by knowing typical bond length, right? So these are typical values for this correction. And interestingly, and this is a quantum behavior by the helium, that the helium, even though, that's the smallest of the noble gases, it actually behaves as if it was larger than neon but then smaller than argon. And you can see that, but for the rest, if you go to larger and larger, then neon is smaller than argon, and that is smaller than krypton, and then xenon is even larger. And you can see also that, remember when we were going to it's probably Chem23 or high school chemistry, how the atomic sizes change when you go into within a period. But anyway, so you can see this relationship here in the experimental values for this correction B. Okay, so this was one of the correction. That was the volume of the particles, and that was a B. And then you can kind of realize that if there's a B, then there's probably an A somewhere, right? And so you can take the correction for the attraction between the molecules into account. And so how would that change it? Well, let's see how this correction will go which way. Well, the total pressure, the observed pressure, that is the particles exerting this pressure on the wall, would be reduced by the attraction, right? Because then instead of, hitting the wall at full force, let's say if I'm walking around in the room and hit the wall because I'm just deeply in my thoughts, but then somebody comes here and distracts me and start an interaction, I will slow down and hit the wall a little bit less. And so this correction is going to be a negative correction on the pressure. Now, how much is this correction? Well, the correction depends on how many interactions there are. So it will be the number of interacting pairs. And then here, that's the important part, the pairs. How many pairs do we have? Well, it's what is the concentration of particles, and then what is the concentration of the other particle. And they're both n over m, right? And so you take this n over m, that will be over one particle, and square it because you need two particles in a given volume for interaction. And so this correction should scale with that. And if you put that into the correction and then put in a constant, that will be, the scaling factor for the n over v squared. Put that in, you get a whole new expression that takes both the interaction and takes the volume of the particles into account. And then another way to write it up would be that pressure plus the correction, volume minus the correction, so that the available volume equals nRT, and then this will be a real gas law instead of the ideal gas law, and then this is the van der Waals equation. And so you have a list of the A correction factors and B correction factors, and let's just take a quick look at whether it makes sense or not. Again, we expect a larger interaction, a bigger interaction for bigger particles. Let's just compare here the noble gases, and you can see that the size of the electron cloud determines the interaction between particles by dispersion. And so xenon has a large polarizability, and therefore the interaction between two xenon atoms is much stronger than, let's say, between two krypton and two argon. Okay. And so this kind of makes total sense. And also you can see that the water, which is a highly polar molecule, it has a high interaction from actually a much larger but then not polar CO2. Okay. And then again, this is the, on the right hand side, this is the size. Now, how then does this deviate from ideality? It's more pronounced at higher pressure, right? Because at the smaller container volume, let's say this is the volume of an individual particle and this is the available total volume, then you can see that as you compress them, then suddenly their volumes become much more important. Okay, so it's more pronounced at high pressure and it's less pronounced at higher temperatures because, again, what you can see is that the pressure at high temperature would be larger, and so this correction factor would be actually smaller. As we move faster, then the interparticle interactions are less important. There, and then this is the characteristics of real gases, and then these are some examples again here, and then you can use this real gas law by simply putting in these constants, the A and B. Again, this taking into account interparticle interactions, and this taking account the individual volume of the particles, which reduces the available volume for them. Okay, so this was the theoretical part of the chapter, and now we have just very little left. I'd like to talk a little bit about some of the important chemistry going on in the atmosphere, but again, this will be very, very little. And now the rest of the chapter will be about some atmospheric chemistry. So we'll be talking about the chemistry of the atmosphere, and of course, for us, most of the gases chemistry is, of course, in the atmosphere. And the principal component in the atmosphere are nitrogen and oxygen, and they roughly have a 78 to 21%. This is by mole fraction, by the way. And other minor components would be argon, CO2, and probably this number is actually much larger by now. We've heard about global warming and climate change and all. But another principal component which is not listed in this table is, of course, water. And the amount of water in the air that changes very much between when you're talking about an arid country, or if you go to the East Coast, let's say North Carolina, in the summer is terribly humid, and so there's a lot of water in the air, then and there are other trace components in the atmosphere. And the atmosphere, of course, is very important, the part that we breathe in. But also the upper atmosphere is terribly important because there are various chemical processes going on there that shield us from high energy radiation. So really the atmosphere is a shield for us. Otherwise, we would probably not exist here. And so that's why it's important to understand what's going on in the atmosphere and how human behavior alters it. So the main sources for air pollution is transportation and electricity production. And we'll take a little bit of a look at both of them, or what are the main issues there. As you know, that combustion of petroleum makes CO2, of course, carbon monoxide and various nitrogen oxides, and then unburned petroleum molecules are left over as well. And this mixture undergoes complex reactions. And so in some big cities, they have these monitoring stations out there that show you the percentage of carbon monoxide, ozone, and then various nitrogen oxides as a percentage of the the health limit. And then these levels actually depend on a lot of different things, the amount of traffic, and also the time of day because of the daylight. And so this picture here, for example, shows the concentration on the y-axis and the time of day on the x-axis, and you can see that the unburned fuel goes way up around the rush hour, and then nitrogen oxides come up at the same time, and then there's different time concentration profile for nitrogen monoxide. And nitrogen dioxide, ozone, comes up when the irradiation is stronger. So how does that happen? Well, NO2 under the photon, under an irradiation, falls apart into nitrogen monoxide. And the oxygen atom, which of course is a radical, right? So that's very, very reactive. And when it reacts with another O2, then gives you ozone. But then the NO2 is regenerated because nitrogen monoxide, when it reacts with O2, it gives you back the NO2, which is then recycled. And so there's this complex interplay between the various components, depending on the temperature, depending on the amount of irradiation, that influences the concentration of various pollutants in the air. And we call this photochemical smog. You obviously understand the chemistry part, and then photo means that a lot of this chemistry is happening under an irradiation with photons, with light. And this is a picture in, I think it is LA, and you can see that the brownish color of the nitrogen dioxide is quite visible here. Now, what about pollution is coming from electricity production? And the principal player there is sulfur, right? So coal, all flavors of coal contain significant amount of sulfur. By the way, petroleum products do too, and that's why when you see low sulfur, I guess highway diesel or something, that means that the sulfur concentration has to be so low, so that when you burn it in the truck engines, then there's minimal pollution coming from that. But coal contains quite a bit of sulfur, which first turns into sulfur dioxide, but then it can further oxidize into sulfur trioxide. And the important part is that the sulfur trioxide, you can simply add it up with water that gives you sulfuric acid. And so in the atmosphere, then the sulfur trioxide dissolves in these droplets of water, and then it gives you acid rain. And then this is a nice pictorial representation of how the acidic gases go up in the atmosphere, and then they dissolve in rainwater and then come back to us as acid rain, which kills plant life, pollutes rivers, streams, and erodes stonework. So this is a good illustration. This was only, I think, like 100 years back, and now because of the acid rain, you can see that the features on her face have been deleted by the effect of the acid rain dissolving the marble. And so this is a map of the acid rain in the U.S., and you can see that in the Midwest, where there's a lot of industry that would cause this, and then that's where we have the lowest, most acidity in the rain. This is a measure of the pH. We'll learn about the pH a lot more later, but you know that the smaller the pH, the more acidic. So this is the most acidic, and you can see that you have the biggest problem with acid rain over here. And so what you want to do is you want to remove the SO2. And so what you can do is if you blow powdered carbon dioxide into the combustion chamber, what happens is the carbon dioxide, calcium carbonate will fall apart into calcium oxide and CO2, and then the calcium oxide reacts with the sulfur dioxide and then takes it out and then deposits as calcium sulfite, and then what you do is then you inject water, and that will remove it in a slurry. And this is what we call clean coal. And then clean means that most of the sulfur oxides are removed. And this is actually a problem, because this was so successful that in the 80s, or actually it was the late 70s, so it was coming up in the 80s, but the decision was made in the late 70s, when they had, when there was a shock of the oil prices suddenly ballooning. And then the country had to make a decision whether go towards more nuclear or more of this clean coal. And then the Carter administration made the decision to invest significantly clean coal, and then going towards electricity production coming from coal. And now that global warming, climate change is a perceived issue, then this decision, of course, is deeply regretted. All right, this is how much I wanted to tell you just very quickly about the chemistry of the atmosphere. But the big part of the chapter was, of course, doing calculations, figuring out how the pressure, volume, temperature, and the moles of a gas are interconnected through the ideal gas law. And so be proficient in doing any sort of a calculation there, also including gas stoichiometry, right? So now, since from the PV equals nRT we could get the molar volume, that would give us a way to put gases into stoichiometry problems. And then we spent a significant amount of time, but that was mostly to give you a background on where this is coming from, why gases behave this way. So we spent some time on the kinetic theory of gases, and that is really mostly for your understanding. And then the one direct result of that would be rate of diffusion. So those equations you would have to know. But as for the kinetic theory of gases, this is more like to understand really what's going on. But we won't be doing calculations with that in the exam. So thank you for watching. This was Chapter 5, Gases in Chem 25. Thank you.